In this lesson, we're going to be looking at some application problems called related rates. Now, here's an example of a related rate problem. If air is being pumped into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. Now, let's take, for instance, if the air going into the balloon is a constant rate. Think about what's happening with the balloon when you just start blowing it up. The radius is increasing rather quickly, but as time goes on and the volume of the sphere is getting bigger and bigger, the volume of the balloon, the radius, the rate of change of the radius would slow down. So the rate of change of the radius is changing, but we said that the air going into the balloon is a constant rate. And that's the idea behind a related rate problems. We're looking at comparing quantities together. And so typically one of them will be a constant rate of change and the other one will be a variable rate of change. And a lot of times it's easier to measure the constant rate of change rather than the variable rate of change. As with this example, it probably would be easier to measure the rate of change of the volume rather than the rate of change of the radius. Now, in a related rate problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. The procedure is to find an equation that relates the two quantities and then use the chain rule to differentiate both sides implicitly with respect to time. The problems that we're going to be working with, the related rate problems we're going to be working with, we're always going to differentiate with respect to time. Let's look at an example. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? I like to create three columns, and let me show you how I create those three columns here. I like to list the given information. I like to list what we're trying to find, and then I have a column for the equation that we need to relate the two, or relate the variables together, so that we can find the derivative of that equation to get our related rates. So the given information in this problem, it says air is being pumped into a spherical balloon so that its volume increases. So I'm going to represent the volume of the balloon as V. So V is the volume. So the rate of change of the volume, I would say, is dV dt. That's the rate of change of the volume. And it says the rate of change of the volume is 100 cubic centimeters per second. Now, what are we trying to find? Typically in these type of problems, you can go to the last couple of sentences to find out what you're trying to find. In this one, it says, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we are trying to find the rate of change of the radius with respect to time. So that would be dr dt. Now, when we fill out this find column, we just discussed a few minutes ago that the rate of change of the radius is changing. So we would have to know a specific point or time that we want to find the rate of change of this radius. Well, in this problem it says find the rate of change of the radius when the diameter is 50 centimeters. So in this category, I always write down when to remind myself there's a specific point in time when we're trying to find dr dt. In this case, it's when the diameter is 50 centimeters. So we have our given column and our find column filled out. Now we need to come up with an equation that relates our variables v and r together. Well, thinking about this problem, we're working with the volume of a sphere. So if we looked at the volume of a sphere, that's 4/3 pi r cubed. And we can see that equation relates the volume and the radius. Now, once we have our equation that relates our variables, we take the derivative of both sides of the equation with respect to time. And I call this the related rate equation, RRE, related rate equation. That's when we take the derivative of both sides with respect to time. Now, 4/3 pi is just a coefficient, so it's 4/3 pi. Now, r cubed, we're taking the derivative with respect to time. So we'd have 3r squared, and r is some function of time, so we have to multiply it by dr dt. That's applying the chain rule. Now we go back to the problem and look at the information that was given and see what we can fill in here to our related rate equation. dv dt was given as 100 cubic centimeters per second equals 4/3 pi. Now r, we're trying to find dr dt when d equals 50 centimeters. Well, we know that if the diameter is 50 centimeters, then the radius would be 25. So at this specific point in time, r would be 25. So we would have 25 squared times our dr dt. And you can see we have everything except for dr dt, but that's what we're trying to solve for. So if we solve for dr dt, we would have 100, and then we would just divide by our 4 pi over 3 times 25 squared. So we would have divided by 4/3 pi times 3 times 25 squared. And that would be our dr dt. Now, if we were to assign our units, we would have a unit of centimeters per second. And let's write that right over here on this side. I can't write it on the other side there. So that would be our units, centimeters per second. So we solved for dr dt, which answered the question, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? Now, we're going to go through the slides, and it's just repeating the same process that we just used to solve this problem. There's our given, what we're trying to find, and when, and there's the equation that relates the two variables together. And taking the derivative of both sides with respect to t, filling in the information, and solving for dr dt. That's just a simplified form, 1 over 25 pi. All right, car A is traveling west at 50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So let's list our given information. So what we have for our given information, we know car A is traveling at 50 miles per hour. So I'm going to say dA dt equals 50 miles per hour. Now, since we are taking the derivative of some position function, we're getting the velocity. So what does that A represent? A should be some position, because if we take the derivative of a position function, we get velocity. So in our diagram, what does A represent? And let's label that. And it's very important in these problems to label things correctly with the correct information. So looking back up at our diagram, we could let A represent the position of car A. So if car A is here, I'm going to say A represents the distance car A is from the intersection. That's its position function. So now it makes sense if we take the derivative of A, we get the velocity for the car. And likewise for car B, dB dt would equal, and that car was traveling 60 miles per hour. So in our diagram, I'm going to let this distance here represent B. At what the information that we're trying to find, it says, at what rate are the cars approaching each other when car A is 0.3 and B is 0.4 from the intersection? So we're trying to determine the rate of change of the distance between the cars. And if I draw that distance, that would be here. That's the distance between our cars. And I'm just going to label that as X. Now just think about what's happening. If car A and B were, say, 5 miles from this intersection, the rate of change between the cars is going to be very small. But as we get closer and closer to that intersection, the rate of change between the distance between the cars is going to increase tremendously. So you can see that rate of change is changing. So we're trying to find the rate of change between the cars, so that would be dx dt. We're trying to find dx dt. Now, when are we trying to find dx dt? Well, it says when car A is 0.3 and car B is 0.4 from the intersection. So when A is 0.3 miles from the intersection and B is 0.4 miles from the intersection, that's when we are trying to find dx dt, the rate of change between the distance of the cars. So let's see if we can create our equation that relates our variables together now. So we have to relate, we look back into our given and find, and we see we have the variable a, b, and x. So if we look back at the diagram, I think we can see a way to relate those together. We're working with a right triangle, so we could use the Pythagorean theorem. A squared plus b squared equals x squared. Now notice, we're not going to plug in a equals 0.3 at this point or b equals 0.4. Those are plugged in after you find your related rate equation. So the related rate equation, I label that as RRE, related rate equation. We're going to take the derivative of our equation with respect to time. So we'd have 2a dA plus 2b dB dt equals 2x dx dt. And now let's plug in the known information. So at this instant, we're looking for dx dt. We know A equals 0.3 miles. So we can plug that in. And dA dt is 50 miles per hour. Now, looking at this diagram, it appears that the distance between the intersection and the car is decreasing. So I'm going to say our velocity is negative. If it was heading the opposite direction, away from the intersection, I would say A is increasing, our velocity is positive. So I'm going to say negative 50 plus 2 times B. Now B, we said at this instant, it would be 0.4 miles. And then the rate of car B is 60. And again, we're going to say that's a negative because that distance is decreasing, equals 2 times x times dx dt. Well, dx dt is what we're trying to find. X is not given. However, can we go back to our diagram? At this instant, we know A would be 0.3 and B would be 0.4. So we can relate, let me try to clear that up a little bit there. Okay, so here we know at this instant A is 0.3, B is 0.4. So we can see that we can apply the Pythagorean theorem to find x at this instant. We could say 0.3 squared plus 0.4 squared equals x squared. I was going right towards the answer. Is x squared. And then when we solve for x, we would see x equals 0.5. So at that instant, x is 0.5, so we can plug that in. And then times our dx dt. So we have all the information to solve for dx dt. So dx dt, we would just need to divide both sides of the equation by 2 times 0.5. So if we did that calculation, let me see here, I think I have what that came out to be. And that came out to be negative 78 miles per hour. Because that distance is decreasing, we get a negative value. Another problem. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So let's fill out our 3 columns. So first of all, what's given in this problem? What's the given information? So it says a man walks along a straight path at a speed of 4 feet per second. So that's some given information. Now, I'm going to represent that as dm dt. and that would be 4 feet per second. Now I should be able to identify what does m represent. M must be some position. What is m the position of? Well, it's the position function for the man. And I'm going to have m represent the position of the man from this point on the path that's closest to the searchlight. So this would be m. All right, is there anything else we can list it as given? We could list the distance from the searchlight is from the path, and I'm going to label it in the diagram as 20. So we'll list this distance as 20. It's not picking up over there. But this distance here is 20, the distance the searchlight is from that path. All right, what are we trying to find? It says, at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So we are trying to find the rate of change of the rotation of that searchlight. So if we label the angle as theta, we are actually trying to find d theta dt, the rate of change of the angle of the searchlight. And when are we trying to find that? When m equals 5. I'm sorry, when n equals 15. So what's an equation that's going to relate these variables together? We have in our given, we have m. In our find, we have theta. So looking at our diagram, and if we could clean up that diagram a little bit, we would have this is theta, this is 20, this is m. So we are trying to find d theta dt. So we have to find an equation that relates theta and m together. So if we thought about that for a moment, we probably would come up with, well, we have to use some sort of a trig function. We have the information that is adjacent to the angle, and we want to find the information that's opposite the angle. Well, if we want a trig function that relates the opposite and the adjacent, we'd say the tangent of theta equals opposite m over 20. And there's our equation. So the related rate equation, we take the derivative with respect to time. The derivative of the tangent of theta, secant squared theta. Now here we have to be careful because we have to multiply this times d theta dt using the chain rule equals. Now m over 20 could be written as 1 over 20 times m. So we would just have, when we find the derivative, 1 over 20 dm dt. We are trying to solve for d theta dt. This is what we're trying to solve for. We do have dm dt equals 4, so we could plug that in. So we would have 1/20 times 4. Now we need to find the secant of this angle. And remember, the secant squared of theta is the same as secant theta squared. So if we can find the secant of this angle, we can plug that value in and square it. Okay, so looking back up here, we have at this instant we're trying to find d theta dt. We know m equals 15 at that instant. So now we know that secant of an angle equals hypotenuse over adjacent, so we have to solve for the hypotenuse. So again, if we use the Pythagorean theorem on our right triangle, we could find the hypotenuse. So solving for the hypotenuse, we would get 25. And this is a special case of the 3, 4, 5. The 15 is 3 times 5. This is 4 times 5. And so you can see this would be the hypotenuse 5 times 5, 25. So we know the secant of theta now. The secant of theta is 25 over 20. So that's what we're plugging in for secant of theta. And then we'll square that. So 25 divided by 20 squared times our d theta dt. And now we have all of the information to solve for our d theta dt. So if we solve for d theta dt, we would get 0.128, and it would be radians per second.